All right, so before we get into a deep discussion about ultrasound waves, we first need to understand what waves are in general. So let's take a look here. Let's take a look at some waves in real life. So what are some waves that you know about? What are some waves that are familiar to us? There's actually a lot more waves around us than you might be aware of. There are ocean waves, like if you go to the beach, you'll see ocean waves. There are sound waves. My voice coming across to you through this microphone is actually an example of a sound wave. A microwave, your microwave oven will actually produce waves that are increasing the speed of your food to heat it up. There are light waves, which work a little bit differently from the others, but they are waves still. We have X-rays, we have radio waves, which is why you have to change the frequency in your car in order to receive different channels because they produce waves at different frequencies, and that's why you don't get interference, or you might get interference or that static that comes across in your radio. Seismic waves are waves in the ground that are caused by earthquakes, for example. Eels and earthworms use different types of waves in order to move. Echolocation is a way that some animals can use sound waves in order to place themselves, in order to know where they are in space. And then, of course, the ultrasound waves, where we get to send sound waves through a body, and then depending on their properties of that wave, then we can see the distance and the type of tissue that we're interacting with. So there's all kinds of waves everywhere around us, and it's really important that we understand how these waves work and how we can use them for our benefit so we can see things that are invisible to the naked eye. So first, let's go into different types of waves. There are three main types of waves. I'm only going to talk about two because the third one gets a little complicated when you get into electromagnetic waves. So we're going to stick with transverse waves and longitudinal waves. And before we get into that, we need to define a wave. So what is a wave? A wave is simply the shifting of particles without overall movement. There is a more scientific term for this definition, but this is the simplest way that I could think of it. So basically, these particles are moving, they're shifting, they're causing a shift in the medium, but they themselves, the particles, do not move. So if you take a look at our GIF here, we can see these dark blue dots are the different particles of water. This is a water wave that I've used as an example here. If you look at the one in orange, you can see that its pattern is circular. The particle itself doesn't actually move, even though the wave itself is moving. So although the wave is moving from left to right, the particle itself is simply shifting up and down. It's not moving with the wave. And that's why you see like buoys and things like that. If they're on a water wave, they don't actually move. So that is an example that you can think of. And all of these blue dots are doing it. The one in orange is highlighted for us to better see what's going on. And here again is a comparison of the two different kinds of waves that I mentioned earlier, the transverse wave and the longitudinal wave. So a transverse wave is where the particles are moving up and down, whereas a longitudinal wave is where the particles are moving side to side. Now, this was reproduced with a spring, which can perform both kinds of waves. So you can see the transverse wave, it's going in this direction, and you can see that they're moving up and down. One trick that you can use, if you look at this spring here, if you look at the wave, yes, it looks like it's moving from left to right. That's the direction of the wave, or the wave front. However, if you focus on one individual spring, let's look at this guy here, you can see that it's just moving up and down. It itself is not moving. Although the wave is propagating, this one spring is staying in place. So that's a transverse wave. The longitudinal wave is something like this. This is where there's compressions and rarefaction. So there's places where the particles bunch up together, and then there's places where the particles spread apart. So you can see that the wave is still moving in the same direction as the transverse wave. It still has the same wave front, but it's moving in a different direction. It's moving in a different way. And same thing we did at the transverse wave. If you focus on an individual spring, you can see that it goes back and forth. It's tricky to see with the compressions in here, but it's just going back and forth. It itself is not moving. So those are the two different kinds of waves. Now, why is that important? Because when we're studying ultrasound, we're actually studying the properties of waves. Those properties of waves are what's going to help us to actually use it practically to calculate where those substances are inside the body that we're sending sound out to. Here is an example of a transverse wave that may be a little bit easier to follow. And for example, water waves are examples of transverse waves. So if you go to the ocean and you're looking at the waves, those are examples of transverse waves because the particles are moving up and down. So you can see we've highlighted a couple in red, so you can track them with your eyes, and you can see the wavelength here as it's moving down. And that's what causes the wavefront. That's what causes the wave to propagate or to move in a certain direction from an origin. All right, now that we've looked at water waves, let's take a look at sound waves. Sound waves are an example of longitudinal waves. Longitudinal waves, remember we said earlier, the particles move from side to side. You can see we have a couple that are highlighted here in red, so you can see how they're moving with the wave. So you can see the wave is still moving from left to right, the wave front is still on the same end, but the particles are shifting left to right, side to side to press and push those particles to move in a certain direction. And you can see there's labels down here. There's a couple labels down here that indicate areas of compression and areas of rarefaction. So when you think of like a pressure cooker where you're compressing something, that means that you're pushing things really close together. So in a longitudinal wave, a compression is where the particles are pushed close together. Rarefaction is where they are spread apart. So that's how a longitudinal wave can move. Instead of having this transverse wave where the peaks are called the crests and the lowest parts are called troughs, then they have compressions and rarefactions. Okay, now for simplicity's sake, when we are studying longitudinal waves, when we are going to be studying sound waves, we're going to look at it from a transverse wave viewpoint, simply because it's a little easier to indicate and measure in this mindset. So you can see there's a longitudinal wave that's being created up here, an acoustic longitudinal wave. Acoustic means that it's a sound wave. So you can see that as we're pushing the particles here, we get those compressions, and we get those areas of rarefactions, and they're creating a wavefront, and those particles are moving side to side, just like we mentioned earlier. If we're looking at that same wave from a different perspective, from a transverse perspective, we can see that this is going on here. And this is actually measuring the pressure of the sound. Remember, if you're compressing something, you're increasing the pressure, you're pushing them close together. So that's why it's going to be indicated by a crest on our transverse wave, or a high peak. And on the other end of it, if you compress less, you have lower pressure. That's our rarefactions here. That's going to be indicated by our trough, by our lowest point. You can think of like a water trough for horses. It has to dip down low in order to fill up the water, hold the water for the horses. So that's why they're called troughs. And we have crests at the top. And so when we're studying our longitudinal waves, we're going to be studying them from this perspective. So we're going to draw transverse waves, although sound waves are actually longitudinal. So I want to make that connection very clear. We're going to see graphs and drawings that look like transverse waves, but remember, sound waves are longitudinal. Okay, great. So that's our first video. Make sure to take a look at the rest of them so that way you can understand better how we're going to measure this and how